Time to start. All right. One of the things I noticed after Monday's review and practice problems was I didn't include something. So I'm going to fix that right now. Everybody see my whiteboard? Thank you. All right, let's go through this. And I'll do this one, then I'll give you one to practice. So it says identify the acid base, conjugate acid, and conjugate base in the following. And I give you a chemical reaction. It can be an equilibrium or just a straightforward chemical reaction. What's a conjugate? Two substances that differ by one proton, H plus. But for students, it's easier to say differ by hydrogen, forget about the charges. So let's take a look at this. And let me move this down here out of my way. Now, if we notice, this has a chlorine, this has a chlorine. So these are conjugates. And I'll explain why I'm doing this in a second, maybe 2 seconds. This has a nitrogen, this has it. Notice this is NH3, NH4 plus, so it differs by H plus. Same thing with HCl, Cl minus. It differs by, hold on. Now you know I don't write with blue because I don't do it that way. No, I'm just differs by H plus. Now, if we look at going from this to its conjugate, does it gain a proton, or in your case, hydrogen, or lose it? It loses it. It donates it. What's something that donates something? An acid. Next, when it goes from Y to W, does Cl minus lose a proton or gain a proton? Just count hydrogens, it's gained one. What is something that accepts or gains? That's a base. But on this side, both of these on the right side are called the conjugates. So this would be a base, but it's the conjugate base. Now let's look at X. X going to Z. When it goes this way, X to Z is NH3 gaining a proton. You can think hydrogen, or losing it. 3 to 4, it's gained it. What's something that gains or accepts a proton? It's a base. Now, let's look at the opposite direction. When it goes from Z to X, this way. does this gain or lose a proton? Just count the hydrogens. 4 to 3. It's lost or donated a proton. What's something that loses or donates a proton? That's an acid, but it's on the right side, so it's a conjugate acid. And that's how you do it. All right. Can everybody see the chemical reaction C6H6? Actually, that should be an H5, excuse me, going with NaOH. Do you see that? Everybody, thumbs up, people. Do you see that on the screen? Thank you.
Yes.
All right. Let me just make a quick correction here, which won't change anything. And it's your turn. Label W, X, Y, and Z acid base, conjugate acid, conjugate base. And for all of you who have your webcam on, thank you. For those who showed up, thank you. Did I miss anybody? Okay, who still has their mic on? Or you shut it off. Thank you. Oh, by the way, this would be 1 point each. And a quick reminder from the management me, if you're planning on handing in the extra credit, make sure you do it today or tomorrow morning first thing. It is optional, but you do have to hand it in if you want the optional, if you do it right and get to 10 points. All right, anybody need more time? Thumbs up, people. Are you done? All right, I'm seeing everybody's thumb, so I better get to work. All right, let's take a look at this. First thing I like to do, and it would have, I think you'd like to do too, is identify conjugates. what differs by only one proton, but in your case, count hydrogens. This is 5 plus 1, 6, 5 plus 0, 5. So it still has 6 carbons, 2 oxygens, or 7 carbons, I'm sorry. So those are conjugates. Now, and no, you don't have to show the lines on a test. I'm just showing you. And this X has oxygen, no carbons, and water has oxygen and hydrogens, no carbon. So I now have my conjugates. So now I can find out, first of all, W, going from W to its conjugate Y. See how it loses this hydrogen? It's got 6, now it's got 5 hydrogens. So that means it's lost actually a proton, and that makes it a proton donor, and it's an acid. Now, going from Y to W, it has 5 hydrogens. Now it has 6, 5 plus 1. It's gained a proton. What's something that accepts or gains a proton? It's a base, but on this side, both of these are the conjugates. So that would make it a conjugate base. Next, I'll look at X going to its conjugate. X goes to Z. When it goes this way, it has 1 hydrogen, now it has 2. What's something that accepts a proton? In your case, is count the hydrogens. That's a base. Acid proton donor, or gives it up. Base proton acceptor. Now, we have one left to go. We know what it should be, but let's make sure we're doing this right. When you go from Z to its conjugate, which I unfortunately erased, but there it is, X, it goes from H2 to OH minus. Does it give up or gain a proton or donate a proton? And the answer is it gives up or donates. What's something that gives up a proton or donates a proton? That's an acid. But because it's on the right side, these are conjugates. And that's how you do it. W is acid, X is base, Y is conjugate base, Z is conjugate acid. And that's how you do it. And now I've kept my promise that I've covered everything at least twice or 3 times. I felt bad when I realized I didn't have a problem on the problem set. I forgot to talk about that in the review. Well, I've corrected that mistake. Thank you. You're welcome. Any questions on that? And I have a request, instant replay, and the answer is uh-oh. The answer is yes, I can. So let me do another one. And there you go. Identify A, B, C, and D, acid, base, conjugate acid, conjugate base. I forgot to mention this morning, I did Thursday's lab today or tomorrow. I'll do Friday's lab. I've uploaded all the points I have for all your labs up through the lab that you handed in last week. You might want to check to make sure things you've handed in, you got points for. Like I said, I've done Thursday, tomorrow, before Friday's lab, I'll do Fridays. Don't forget, get the lab due this week in on time, please, or you lose 10 points. Remember, count hydrogens, forget about H plus. Anybody need more time? Let me do the new fashioned way. Time for everybody to vote. All right, looks like everybody's done. Let me get going. All right, let's look at where are the conjugates. This has a sulfur, this has a sulfur, D does not, so they're going to be conjugates. This has no sulfur, B, KOH, potassium hydroxide, and D has this oxygen. They only differ by H plus, or in your case, count hydrogen. So if we go from A to its conjugate, C, what happens when you go from A to C? You have two hydrogens, now you have one, it also has a charge. So it gave up a proton or hydrogen or donated, that's an acid. Going the other direction, from C to its conjugate, has one hydrogen, now has two. What's something that accepts a hydrogen, actually a proton? That's a base. Now on this side, both of these, you can immediately write conjugate. That's by definition. Now, if we look at, oops, I made a mistake here. Base. Now, let's look at the other. If we go from B to its conjugate D, going this way, one hydrogen, it's picked up a proton, but for students, just count the hydrogens too. What's something that accepts a proton? That's a base. And if we look at going the other way from D to B, has it gained a proton? H, count the hydrogens, are lost. 2 to 1, it's lost a proton. What's something that loses or donates a proton? That's an acid. So A is an acid, B is a base, C is the conjugate base, A is the conjugate acid. And that's how you do that. Everybody clear on that now? If not, go back and watch the video. I should have it up by tomorrow. Well, you shouldn't be. For the test, you should not be watching the video. By the way, I know if people are or not, so don't. There are things about YouTube I know you don't. All right. I'm going to skip chapter 16. We'll come back to that. I'm going to do chapter 17 now. I'm going to teach you everything you need to know about nuclear energy in about 20 minutes or less. I could spend a whole 2 semesters teaching this nuclear energy, but we're going to do it real quick. And this will not be on test number 4, but will be a few points on the final. Speaking about the final is coming up. Sometime over the weekend, I'll post the point breakdown from the final. It'll be comprehensive. Now, to make your life easier, don't tell anybody, I'm being nice. The first part of the final will be stuff from test number 1, second part from test number 2, then 3, then 4, then a few points on nuclear chemistry. Now, I would highly recommend, since you all have them and I've gone through the answers, that you, by the way, I don't charge extra for children. But anyways, by the way, I would recommend you use your tests 1, 2, 3, and 4 as practice problems for the final. Will I put the same questions on the final on the test? No. Will I put similar ones? Well, look at the practice problems. They were similar. So the tests are your best practice. And I will tell you this, next week, I'm going to spend a whole week on review the whole semester. I highly recommend you come to class. And this way, you'll be prepared for the final because you'll have a couple hours studying review with me, Dr. White. And that's why students do well on my final, those who show up. All right, let's go to all right, thumbs up, people. You see chapter 17 on your screen. Thank you. All right, switches off on this slide. We're going to talk about nuclear radiation and nuclear chemistry. And what is a radioactive element? It's an unstable isotope of an element that will emit energy spontaneously to form a more stable isotope. Remember, isotopes have the same number of protons and electrons, but different neutrons normally. Now, the energy emitted from an unstable isotope, otherwise known as a radioactive element, Shay asked the question, will the final be timed? And the answer is sort of. It'll be the same way. If we were in a classroom face to face, we'd have an hour and 50 minutes. Most students, like almost all of them who take my final, when I teach Chem 1211, I've been doing it enough years, I know what I'm going to tell you is true. If you study, most students, even though you get an hour and 50 minutes, are usually done in about an hour and 15 minutes, hour and 25 minutes. You, like my test, you have plenty of time. Now, for the final, I'll give you 3 or 4 hours, whatever. It's one of those things, unless you cheat, which you shouldn't. I know if you do, and you don't want me to do, no, because I'll do what's in my syllabus. And you don't want that done ever. I don't want to do that ever, but I've done it. If you study, you'll do well. If you haven't, you won't. Simple as that. And just like the hourly exams, I'll give you, during finals week, we have no class. What I will do is the beginning of our time slot, I think it's Monday at 10 a.m. of finals week, I will send out we won't have class then. I will send out the password and you'll have until the next morning to do it and upload it. I could make it by the end of the finals, but if you have internet problems, then what do? And that's happened. It's happened to Dr. White this semester. All right, let's get back to nuclear radiation. All right, so switches off. There are different types of particles or energy, radioactive energy. Switch is totally off, and you can go back and review this if you need to learn more about it. There's something called an alpha particle. An alpha particle contains 2 protons and 2 neutrons. and it's emitted by radioactive nuclei. And it obviously has a positive charge because protons have a positive charge, neutrons no charge. Next, there's a beta particle. Now, this always amazed me because a beta particle is a particle whose charge and mass are identical to the electron. Why don't you just call it an electron? Well, radiation chemists or nuclear chemists don't. They call it a beta, and it's also emitted by a radioactive nuclei, which is what we call an element that's radioactive. And obviously, it's the same charge as an electron mass, and it's got a negative charge. It's got a negative charge. Now, positron is a particle produced by an unstable nucleus like a proton, and it has a positive charge. Why don't they do call it sometimes? And finally, gamma rays are high form of energy without mass or charge that's emitted by radioactive nuclei. How can something not have mass or charge? Well, light doesn't have mass or charge. The radio waves for your radio or your cell phone don't have mass or charge. By the way, in our universe, gamma rays will kill you. They will not turn you into the Hulk. Now, radioactive decay is the process, again, switches off, process whereby a radioactive nuclide is transformed to nuclide of another element as a result of emission of radiation. And these can be alpha, beta, or gamma rays, which are all lethal to our life, which is why you don't want to be near something radioactive. All right. Everybody, I am turning the switch on. This will be things that I can put on the final. It will not be on test number 4. Let's talk about the rate of decay, otherwise known as the half-life of a radioisotope. And the half-life, which is defined as T1 half, or symbol T1 half, is the amount of time required for 1/2 of any given quantity of a radioactive substance to undergo decay. And notice I have know this. Let me make it official. Know this, that the rate of the half-life of a radioisotope radioactive element is the time it takes for half of it to decay. And let's look at, what does this mean? Thumbs up, people. Do you see 4.5 billion years on your? What that means is uranium-238 or other radioactive elements have very long half-lives. If you had a ton of uranium-238, it would take 4.5 billion, yes, billion years before you'd have 500 pounds of it. Half of it decays into something non-radioactive. Let's see if we can find some other ones. I'm looking right now. I'm not finding what I'm looking for. But anyways, this has important implications. Now, if you live in Illinois, which I think all of you do, guess what? We have nuclear energy. We make electricity by the nuclear radiation, heating up water, making steam, turning a turbine to make electricity. Well, that means is you're going to get nuclear waste, and the waste is going to stay radioactive for millions of years. And what if you look online, you can read about this for many, many years. They've been storing those wastes at the plant site, and it's not going away in our lifetime. In terms, unless somebody comes up with a way, and I've thought about it, I don't know where. I'm not a nuclear scientist. That's not my training, but there's one by Lake Michigan by Northwestern that's been closed for years, but the nuclear waste is still stored on there. Now, interesting thing, a number of years ago, our government, someone in our government decided, I think it was under Bush, I'm not sure, the last Bush, and that was not the first one, that let's dig this big hole in these really stable mountains or underground rock formations right outside of Las Vegas and store this stuff from the whole United States. And it's just out in the middle of nowhere and it'll be safe. Well, first of all, people that want that in their backyard, I wouldn't. I can't blame them. Everybody see Yucca Mountain Nuclear Waste Repository? Well, the government decided to do this and they spent, I don't know how many billions of dollars. And they came up with these really fancy containers that they said, I don't know if you can see it. Let's see. They dug this hole in this Yucca Flats outside of in Nevada, and they came up with these containers to put all the radiation in. And besides the local people not wanting it, you notice they already spent a lot on test facility to dig underground and have vents. Well, this stuff I'm looking for and I don't see it. Anyways, this stuff had to stick around and be safely contained for 1 billion or 2 years or longer. So they put some stuff in these fancy new containers, and within a year or two, they're leaking. Right, it's going to hold up for 1 billion or more years. Well, the whole thing got scrapped, and we still don't know what to do with nuclear waste. Somehow, somebody should find a way. How can you safely, quickly, without doing harm to everything, make it decompose? Well, nobody's found that. But what I do want to show you about half-life is the following. Instead of learning a fancy equation, Hang in there. All right, thumbs up, people. You see 4 points on your screen? All right, let me decode it. I made up a new chemical. Thursdonium has a half-life of 4 years. If you have 1,600 grams of thursdonium, then how much thursdonium do you have after 12 years? Now, you can learn a fancy equation, but if it's an even number like this, which I will do on a test, if I put this on a test, how do you do this? Well, let's call it TH. You have 1,600 grams. Its half-life is 4 years. So after 4 years, you'll have half of that, 800 grams. Another 4 years, you'll have half of that. You'll have 400 grams. Another 4 years, because we're doing 12 years, so 4 plus 4, and we need another 4, you'll have 200 grams. So at the end of 12 years with a half-life of 4 years, you'll have 200 grams. And that's how you can figure out half-lives when it's simple, straightforward like that. Now, if I give you 3.5 years, or say after 7 years, then you'd have to use the formula. Dr. White doesn't remember that formula. Anyways, you round it off. And that's half-life. And half-life for certain radioactive elements that are used to treat people with cancer have a very tiny half-life. So if it's injected into your body, within a couple weeks, it's gone, or I don't know, I'm not an expert in there, but it's not going to be around your body for 1 billion years, because you aren't either. I'd like to, and I'd like you to be too, but we're not. All right, let's continue on. And you should know how to do that. Next week, I'll practice that with you again. All right, switches on big time. There's 2 types of nuclear reactions. One is called nuclear fission. The other is nuclear fusion. You should know that nuclear fission is the process in which a large nuclei, something with a high atomic number, splits into medium-sized nuclei. And when it does that, it releases free neutrons and a lot of energy. This is an example how uranium works. When it undergoes nuclear fission, it becomes smaller things and gives off a lot of energy. Now, you should know an example. Where do we use nuclear fission? In a nuclear reactor. So when we're making energy, with nuclear fission, the letter I gives it away, and I'll explain how you can tell the other one from this one in a little while. You should know what's an example of nuclear fission. Again, this won't be on test 4, but it can be on the final. Now, the other type of reaction, nuclear reaction, is nuclear fusion. And here, that U gives it away. Fusion. Why? Because that's how the sun makes energy. It undergoes on the surface or underneath the sun. You have nuclear fusion going on. And what is this? This is the process in which nuclei are put together to make larger ones. And hydrogen plus hydrogen are slammed together to make helium plus lots of energy. That's better. And you should know nuclear fusion. I always think, oh, you and fusion, That's what's happening on the sun. That smaller nuclei or atoms coming together to make larger ones and energy. So let's go back and review. Nuclear fission is where you have a large atom splitting to smaller ones in energy. This happens in a nuclear reactor. And fission doesn't have a U, so that's not what's happening on the sun. And it's happening in our nuclear reactors. And for the nuclear fusion, U, like in the sun, U, that's when you have smaller nuclei are put together to make larger ones. How many of you looked up the sky and seen the sun, thought that's a big monster chemical reaction, radioactive chemistry going on right before your very eyes? And that's it. I'm going to do something unusual today. I'm going to end 2 minutes early. And with that, I'm done. Don't forget, in a little while, I'll be sending out the password for test number 4. And you have till tomorrow to upload it. Do not cheat. Please don't. I'll know if you do. And for those who have lab on Thursday, I'll see you Thursday. For those who have lab on Friday, I'll see you Friday. If you have any questions this afternoon or tonight, email me. Tonight I'll be in my office hours. And with that, gang gesund, be healthy. Don't forget to get your shot, vaccination if you haven't. I've gotten both of mine, so I'm good to go, even though I'll still wear a mask. Bye now, gang gesund.